Hello, everyone. Welcome back to lecture 3 of this thermodynamics module. Today, we are going to talk about thermodynamic relations and equation of state for fluids. Just a quick recap of our lecture 2. So lecture 2 would define two heat capacities. One is constant volume heat capacity, CV, and then the other is constant pressure heat capacity, CP. For ideal gas, we know CV and CP are just constant values for monatomic gases. CV is equal to 1.5 times R. For diatomic gases, CV is equal to 2.5 times R. And then for CP, for ideal gas, it's just equal to CV plus R. So for monatomic gases, CP is going to be 1.5 plus 1 times R, meaning 2.5 times R. And then we went ahead to talk about the heat engine. Heat engine is used trying to convert heat to work, right? Specifically, we talked about the Carnot cycle heat engine, which involve four reversible processes. One, isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression, right? All these are four reversible processes. And the way these reversible processes ensure that Carnot cycle heat engine actually has the highest efficiency possible, right? And then this efficiency we said is going to be 1 minus Tc divided by Th, and this efficiency will always be smaller than 1, meaning that no perfect engine is available, just like converting heat 100% to work. That's not possible. So that's essentially the second law of thermodynamics, right? Because a Carnot engine already give you the highest efficiency, which is less than 1. So all other engines will be efficiency will be less than 1. So they cannot convert heat 100% to work. Okay. And then alternatively, we can also state the second law of thermodynamics in terms of like entropy. Entropy tend to increase. And then basically heat flows from always spontaneously flow from hot to cold, not the other way around. And then by definition, ds, S is entropy, ds is just equal to dq. Remember, this Q has to be reversible heat, right? dq divided by T. And then we said entropy is a thermodynamic property, so delta S is just equal to integral dq divided by T. And then for second law of thermodynamics, delta S is always tend to increase. And for adiabatic process, dq is equal to 0. If this process is reversible, then delta S is equal to 0. But if it's an irreversible process, then delta S is going to be greater than 1. Now, today's lecture, we are going to talk about thermodynamic relations. Basically, what we are trying to do here is combining first and second law of thermodynamics, trying to get some fundamental thermodynamic relations, right? So by the end of this lecture, you should be able to understand the thermodynamic behavior of fluids and how they connect to internal energy, entropy, and enthalpy. And then we are going to talk about thermodynamic relations and PVT behavior of fluids. And then really trying to talk about the compressibility factor Z, which quantifies the deviation from the ideal gas behavior to real gas behavior. And then that this difference is also quantified by residue properties. And then departure function from ideal gas. All right. So now just a quick recap from lecture 1 and lecture 2. Lecture 1, we talked about the first law. First law, the differential form of this equation is du equal to dq plus dw. And then we know dw is equal to minus pdv. So this is the first law. Okay. And then the second law is basically dq is equal to T times ds, right? Remember, ds is equal to dq divided by T. So you move T to the other side. Now, what we are doing here right now is basically replacing, substitute dq equal to TdS into the first law, meaning that we are combining first and second law. This is what we are going to get. du is equal to TdS minus PdV, right? And then you can also divide, you can rearrange the equation, moving ds to the other side, but divide by t on both sides, right? So here ds is going to be 1 over t du plus p divided by t dv, okay? So now if you look at this equation, right, you have internal energy, temperature, entropy, pressure, volume, molar volume. And all these are thermodynamic properties. We have a total of 1, 2, 3, 4, 5. 5 thermodynamic properties, right? So this equation actually give you the relationships among all these thermodynamic properties, right? P, V, T, U, S is contained in this single one fundamental equation. And this fundamental equation is again combining first and second law. So basically this equation is always true, right? And then now we also talked about the enthalpy, right? And this enthalpy is a new thermodynamic property that we define. And basically this new thermodynamic property are just going to be a relation between these primary thermodynamic properties. So these five are the primary thermodynamic properties, right? H, remember H is equal to U plus PV. So basically, any new thermodynamic property that we are going to define or we already define as enthalpy is just going to be the relationship between these five thermodynamic, a few of these five thermodynamic properties, okay? All right, and also you will see, right, T always go with S, and then P always goes with V. So these, you can say these are conjugated pairs. Conjugate pairs, T and S, we call it a thermal pair because it's related to heat, right? So dq is equal to TdS. So T and S is a thermal pair. And then here you can see minus P and V. Usually we call this as a mechanical pair because it's related to mechanical work the system is performing, right? dW is equal to minus P dV. Okay, so P and V are a conjugate mechanical pair. Okay. Now, we already defined enthalpy, right? So just recall enthalpy H is equal to U plus PV. So basically internal energy plus mechanical pair, right? And then, mechanical pair is minus PV, so you have like a minus sign in front, okay? So U minus mechanical pair. And then now, similarly, we can define two new thermodynamic properties. One typically people use is called Helmholtz energy. So A is usually used to represent this energy. Okay, so A is just equal to internal energy minus thermal pair. Okay, so U minus TS is your Helmholtz energy. And then the other most important, very important thermodynamic property is called Gibbs free energy or Gibbs energy. And G is usually used to represent Gibbs energy. So Gibbs energy is just enthalpy minus thermal pair. So H minus TS, okay? And then if you plug H back into this equation, so it's going to be U minus mechanical pair, and then minus thermal pair. So H is U minus mechanical pair, A is U minus thermal pair, and then G is basically U minus both mechanical pair and also thermal pair, right? This is like more straightforward to understand, to remember, okay? All right, so these are the definition of these three additional thermodynamic property in addition to those five primary thermodynamic properties, okay? Now, these are the definition. We can also go ahead and do the differential form of these energies. So dH is going to be equal to du plus dpv, right? So this is your differential form. You can from combining first and second law, we already know how to combine du. Du is equal to TdS minus PDV. So this is like from the previous slide. And then here dPV is basically, we are just like splitting them out. So dPV is equal to VdP plus PDV, right? And then if you combine these things, right, together, in the end, you will get TdH is just equal to TdS minus PDV plus PDV, they will cancel. So in the end, DH is equal to TdS plus VdP, okay? So this is your differential form for enthalpy, right? DH is equal to TdS plus VdP. And similarly, you can do the same things for dA and dG. What you can get is dA is going to be equal to minus PDV minus SDT. And dG is equal to VdP minus SDT, okay? As you can see, right, TS, they always go together. V and P go together. Minus V, minus P, V go together. ST go together. B, P, S, T, right? So these are the reasons why we need to define, right, thermal pair and mechanical pairs, okay? So all these are just like the thermodynamic relations, okay? Now, I just like give you a quick summary, right? Fundamental equations, right? Internal energy du is equal to TdS minus PDV. Again, it's combining first and second law, so this equation is always true, right? Enthalpy is basically you are adding things on top of each other. So all these are always true, right? That's why we call these our fundamental thermodynamic equations, okay? Always holds. These are all from combining first and second law of thermodynamics. And then now mathematically, you can actually look at this differential equation, and then you can consider this is a partial derivative with respect to S holding V constant, right? For Maxwell relationship, basically, this is like the first derivative, and then we can go ahead to take a second derivative. So basically, you take this guy, and then you take derivative with respect to V, second derivative with respect to V while holding S constant, right? So it's basically this is what we are talking about here, right? Is going to be equal to minus P. Again, minus P is first derivative of U with respect to V while holding S constant. But now if you are taking a second derivative, it's going to be minus P taking derivative with respect to S while holding V constant, right? So the second derivative of those should be equal. That's why partial T, partial V, S is going to be equal to minus partial P, partial S, V, holding V constant, right? So now this is this is called Maxwell relations, okay? And then this Maxwell relation is directly derived from this internal energy differential equation. And similarly, we can get another Maxwell equation relation from enthalpy equation. So basically, partial T with respect to partial P while holding S constant is equal to partial V partial S while holding P constant, right? Similarly, from Helmholtz equation, we can get like partial, you have minus sign, so they cancel. So partial P, partial T while holding V constant, partial S, partial V while holding T constant. Same thing for Gibbs free energy. So partial V, partial T while holding P constant is equal to minus partial minus S, right? Minus goes to the front, partial S, partial P while holding temperature constant. So these are all the Maxwell relationships that you can quickly write out if you know the fundamental equations, okay? This is just like mathematical treatment. Okay. All right. So the reason why we want to use these Maxwell relations is basically we want to convert variables. Okay. So if you think about like G here, Gibbs free energy, right? You all have like just like if you do the integration, right? P and T is your variable. So in the end, G is going to be a function of T and P, right? If you know V and S. Okay. So in this case, right, G is going to be a function of T and P, temperature and pressure. And then temperature and pressure are measurable variables, right? You can use a thermometer to measure temperature. And then you can use a pressure gauge to measure pressure easily. So this way, we can actually quickly calculate, right, what is your G, okay? Now, the reason why we use these Maxwell relations is that at the end, what we are trying to do is that we are going to combine fundamental equations plus Maxwell relations. And then we are trying to convert everything, S, H, U, A, G, right? Now here, U is going to be a function of S and V. But through Maxwell relations, right, you can actually eventually convert U into a function of T and P, okay? Same thing for H, originally as S and P. And through this Maxwell relations, you can actually convert H to a function of T and P as well, okay? So that's our goal, right? But we are not going to give you all the detailed math. If you are interested, you can read the additional slides, but we are going to skip a lot of math and then give you the answers, okay? So if you go through the fundamental equation plus Maxwell relations, do some math, eventually you can get this, right? ds in the end is going to be Cp dt divided by T minus partial V, partial T, holding pressure constant, dP, okay? So this is your ds. And then here you can see S is now converted to T and P variables, okay? And then same thing for du. Du is more complicated. So du is going to be Cp minus P times partial V, partial T, holding P constant, whole thing times dt plus minus T partial V partial T, holding P constant, minus P partial V partial P, holding T constant dP. Again, same thing, right? U is converted to a function of T and P, okay? And now dH is equal to Cp dt, right? Plus V minus T partial V partial T, holding P constant, dP. Again, H now is dt and dP, so a function of dP. So if you look at these three equations, right, you all have like Cp in this equation. And then you all have like VTP, 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 VPT, VTP, right? So it's just like different combinations of PVT, okay? So if you look at this, right, now if I want you to calculate what is the change in entropy between state 1 and state 2, right? If we specify state 1 is P1, T1, V1, and state 2 is P2, V2, T2, right? Now you, because this is state change, right? We are talking about the difference in state. So we just take integral, right? So at delta S is going to be equal to the integral of ds from, right, T1, P1 to T2, P2, okay? So that's what we can do, right? But in order to do that integral, we actually need to know Cp, okay? We also need to know the PVT relationship for this particular system. Let's say if it's a gas, then you will have a particular PVT relationship. For ideal gas, we know PV is equal to RT, right? So now, so this means we can actually calculate delta S, delta U, delta H for any pure substances between two states. right? If we know both CP and also the PVT relationship. Now, the PVT relationship of the system, sometimes it's actually called equation of state or EOS, okay? So for PVT relationship, you can actually measure it, right? Let's say you have like, nitrogen gas, right? You can heat the nitrogen gas up in a chamber to a specific temperature. If you hold the system pressure or external pressure this constant, then the volume will expand or shrink, right? You can actually measure V as a function of TP and then figure out the PVT relationship, right? So this equation of state, you can actually measure it. And then for ideal gas, like I said, PV is equal to RT or V is equal to RT divided by P, okay? And then for CP, CP is sometimes is a function of temperature only, okay? And for ideal gas, you can actually treat them as constant values, right? CV is equal to 1.5 times R for monotonic gases, for example, okay? And then for these CP, for real gas, right, then you can, you will have a T function. So this CP value, it's actually tabulated in Appendix C, and we will show you a screenshot in a moment, okay? So basically what I'm trying to say is that the V-PVT relationship is usually given if you specify a substance, okay? And if you specify it's a gas or liquid, usually you will have a specific PVT relationship. And then CP, for a lot of like substances, it's also given, right? So basically, this means that, right, for most of these species, we can actually calculate the changing entropy, internal energy, the enthalpy, right, by plugging in these two into this equation and then take the integral, right? So purely math after that, okay, after you figure out CP and PVT relationship, okay? All right, now, however, we can only calculate delta A and delta G for isothermal processes, right? DT is equal to 0 or T2 equal to T1, okay? Now, this is because when you take integral, you have like, if you convert this S to dt, then you will have 2 dt in the term, okay? So in order to calculate that, right, you have to specify dt is equal to 0, otherwise you cannot calculate that, okay? So only delta S, delta U, delta H, once you know these, you can actually plug in and take the integral, calculate, okay? For dA, delta A and delta G, you have to be an isothermal process in order for you to calculate, right? So here, if it's an isothermal, then it's going to be minus PdV. So this is pretty straightforward to calculate by the integral of that. And also VdP is pretty straightforward to calculate as well, okay? All right. So that's combining first law and second law, right? And then from there, how you can calculate the change in thermodynamics between states, as long as you know the heat capacity and also PVT relationship or the equation of state, okay? Now, just like more details about this heat capacity, like I said, heat capacity is sometimes a function of T. But most of the time, you can actually treat them as or nearly a constant. For example, CP is equal to just like 3.5 times R for ideal nitrogen. So basically nitrogen in the ideal gas state, okay? So for now, for ideal gas, let's just treat CP as a constant value, okay? And then for ideal gas, we already mentioned, right? V is equal to RT divided by P. So this is basically your equation of state for ideal gas. Now what we do is by practice, we are just like inserting our, replacing our V term with RT divided by P in our previous differential equation right here. Basically, d, right? V replacing this V with RT divided by P. Okay, nothing else is changing. Okay. All right, so here we can see, right, partial RT divided by P partial T. So here, right, constant P. So P and R are constant. So basically this is going to be R divided by P, right? R divided by P times P is R. So Cp minus R is equal to Cv for ideal gas. So in the end, so this is like Cv dt, right? And then on here, right, same thing. It's going to be R divided by P, R divided by T in this case, right? Um, and then basically here, this guy, this and this term will cancel. So in the end, du is equal to Cv dt. That's why in lecture 1 or 2, we mentioned for ideal gas, right? Internal energy only depends on temperature, right? This is the reason why du is only a function of, du is equal to Cv dt. Doesn't have like any dp term. So internal energy only change when the temperature changes, okay? And then Cv in this particular case is going to be 2.5 times R, which is Cp minus R, okay? All right. Then we do the same thing for dH, right? dH is going to, from the previous equation, you can see dH is Cp dt. And then again, we are going to replace V with RT divided by RT divided by P, right? So here we can do the partial derivative while holding P constant. So R divided by P, right? Times T, RT divided by P is V, right? V minus V cancel. So basically in the end, dH is also just equal to Cp dt, right? So these are actually the definition of these heat capacity, if you still remember, right? All right. So dH is equal to Cp dt, du is equal to Cv dt. Now, what's about ds, right? Again, ds, we are replacing that V term with RT divided by P. And then here we are taking derivative while holding P constant. So T cancel, right? So R divided by P dP, right? So basically in the end, right, it's going to be Cp dt divided by T minus R times dP divided by P, okay? So this is your ds, okay? Now, basically, you just take the integral, right? If you want to calculate the changes between two states, and then here, remember, Cp is a constant value, right? Then you basically do the integral of this. So delta U is going to be Cv delta T, right? Imagine state 2 has T2. State 1 has T1, so it's going to delta T is just equal to T2 minus T1 times Cv, right? Same thing for delta H. Delta H is going to be Cp times T2 minus T1. And then taking integral of this is going to be, right? So here you have an integral dt, so you have d1 to t2. And then here is basically natural log T2 over T1 for the first term, right? Now, when you take the integral for the second term, then basically it's going to be P1 to P2, right? And then dP, P taking integral is natural log, right? So natural log P2 divided by P1, and then the minus sign is still there, right? So basically, these are how you calculate delta U, delta H, delta S between two states. As long as you know T1, P1 for state 1 and T2, P2 for state 2, you can actually plug in to these equations and you can figure out the difference in their internal energy, enthalpies, and entropies, okay? These equation again, remember these are equations for only works for ideal gas with T independent CP. So basically CP is constant value, doesn't depend on temperature, right? That's why when we take the integral here, we can treat CP as a constant values, okay? Constant value, constant value. So you don't have to worry about T1 changing to T2, okay? All right, so these three equations, you should be able to memorize them, okay? Or at least know how to derive these, okay? All right, so now speaking of like CP, sometimes has a T function, right? So this is like the appendix table, table C1 in our textbook on page 669. So here we are just like saying that the heat capacity of gases in the ideal gas state, right? So sometimes it's a function of temperature, right? So Cp divided by R is actually equal to A plus BT time plus CT squared plus DT minus 2, okay? And from the temperature, so here is the temperature range above 298 K, you can actually use this equation. And then all these are just like different A and B values tabulated for different gases. So basically these values are measured by previous researchers already, and then they tabulate it for you so that you don't have to, redo the measurement, right? So these are experimentally measured properties for your CP, right? Now, if you know a particular CP as a function of T, then you can plug back into this, but while you are doing the integral for this term, then you need to consider CP as a function of T, and then you need to combine with this, right? And then take the integral. And then same thing for this, right? Now CP is no longer a constant value, instead is a function of T. Then you should be able to take the integral of that, okay? All right, I do have like some example in the additional slides. If you are interested, you can take a look at those, okay? All right, so now we have already talked about CP, right? We also mentioned we also need to know the equation of state or EOS, or the PVT relationship of a particular system to be able to solve these, right? So we already talked about ideal gas law, or the equation of state of ideal gas, which is simple PV equal to RT. But what about other non-ideal gases, right? So there are several equations of state for non-ideal gas. Like the first one is called virial equation of state. And usually this virial equation of state is actually can be used to describe many real gases, okay? And then the mathematical form of this is equal to the following. So PV is divided by RT is equal to 1 plus B. B is the virial coefficient divided by V time plus C divided by V squared plus D divided by V cubic and etc. Right? So you will increase in V power, and then you have different constant. Or alternatively, you can write the equation as PV divided by RT is equal to 1 plus B prime times P, because P and V are inversely related, right? So 1 over V is analogous to P, okay? So it's going to be B prime times P, and then C prime times P squared, D prime times P cubic, okay? And then continue on, right? And then B prime is the equal to, if you do the exchange, right? So in the end, B prime is equal to just equal to B divided by RT, and then C prime is equal to C minus B squared divided by RT squared, okay? All right, so this is the virial equation of state for real gas, okay? And now we can mathematically treat this equation a little bit. So basically what we are going to do is that this is basically the actual volume of your real gas. But what if we normalize this actual volume to the ideal gas volume, right? So V normalized to the ideal gas volumes. Ideal gas volume, we already know how to calculate, right? Is V is just equal to RT divided by P, okay? So now this is the actual volume, and then we are trying to divide by the ideal gas volume, and then we plug in ideal gas volume, again, is RT divided by P, and then P goes on top, and then basically is equal to P actual volume divided by RT is defined as the compressibility factor. So Z compressibility factor is equal to actual volume divided by ideal gas volume, okay? And so this is, if Z is equal to 1, then that means your actual volume is equal to ideal gas volume. So that means your real gas is actually behaving like an ideal gas, right? Now, ideal gas usually usually when you talk about the gas at a very high temperature or very low pressure, usually they will follow ideal gas law. By low pressure, I mean 1 atm, right? 1 atm is considered to be a low pressure. You can actually pretty much assume they will follow ideal gas law, okay? And then this Z is basically the ratio between your actual volume with the ideal volume if you have the same pressure and temperature for this particular gas system, okay? Now, like I mentioned, Z is equal to 1, then we are talking about the ideal gas behavior. So your real gas behave like ideal gas, okay? Now, if Z is less than 1, that means your actual volume is smaller than the ideal gas volume, right? Like I mentioned, ideal gas, you have like negligible gas particle volume and also negligible intermolecular interactions, right? But when you have like Z minus smaller than 1, meaning that you may have some attractive interaction, bringing these gas molecule closer to each other. So that means you have a smaller actual volume. Okay, so compressibility is going to be less than 1. So you will have low attractive interaction. And usually this will occur when your gas is at a very low temperature, okay? When you have a very low temperature, so here in this plot, we are plotting Z compressibility factor in your y-axis and pressure on your x-axis, right? And then here, these are curved for different temperature, right? This one is 175 K, increasing all the way to 500 K. So at at low temperature, you can see attractive interaction dominate. So now the gas molecule are brought together closer. So your actual volume is smaller than the ideal gas volume. So you have a Z value that is less than 1. Okay. When you increase your temperature, then slowly they recover the ideal gas behavior, right? Now, if you have like at a very um, high temperature, right, then you have repulsion dominates, and then like these gas molecule doesn't even want to be near each other, right? So in that case, it's going to be Z is greater than 1, right? But the deviation from the ideal gas law, right, compared to lower temperature system is much smaller, right? So usually, like we can see, right, at low pressure but high temperature, right, we can actually say the system is actually behaving like ideal gas law, right? So we are talking about this particular section, okay? So that's basically for a real gas, right? In this particular case, it's methane, right? For real gas, depending on your condition, it can deviate from your ideal gas behavior a lot, right? So here it's actually deviating almost by 50%, okay? All right. So that's virial equation of state. That's like one type of PVT relationship for non-ideal gas, okay? And oftentimes, these higher terms are just like trying to increase the accuracy of this particular virial equation of state. For real world usage applications, usually we can actually ignore these terms, right? As long as you have two terms, your accuracy is pretty good already. Okay. And then mathematically, it will be much easier that way. Okay. So real world application wise, we usually just like, write down two terms here. Okay. Just ignore the terms, higher up terms. Okay. All right. So that's virial equation of state. And the second type of PVT relationship for non-ideal gas is called cubic equations of state. And these cubic equations of state are applicable for both gases and also liquids, right? They are sufficiently general to apply to both gases and liquids, and as simple as possible while providing a reasonable accuracy to avoid computational difficulty. Right, so one subcategory of this cubic equation of state is called van der Waals equation of state. And then basically the mathematical expression for this van der Waals equation of state is P is equal to RT divided by V minus B minus A divided by V squared. Now, we are not going to talk too much about the physical meaning, but this is correcting the particle volume, like gas particle volume, and also correcting intermolecular interaction between these gas molecule. Okay, if you are interested, you can go to the textbook to better understand. Okay, but this is basically the expression for your van der Waals equation of state. Now, the reason why we call this as a cubic equation of state is because when you can rearrange this equation into V squared, V cubic minus V squared plus and then plus A divided by PV minus AB divided by P equal to 0. Now you can see the highest power of this V is going to be cubic, right? So that's why we call this as a cubic equation of state. Okay, so that's van der Waals equation of state. It has physical meaning behind of this equation. Okay, deviating from ideal gas law. Okay, the second subcategory of this cubic equation of state is called Rayleigh-Hwan equation of state. And then similar format, you will have P equal to RT V minus B and minus A times, now you have also some temperature coming into play, right? Temperature 1/2 V times V plus B, okay? And then here, A is a value depends on temperature and critical temperature and critical pressure for a particular system, right? TC, PC value, you can actually look them up. So these, as long as you specify the species, A is a constant, okay, for that species. And B, same thing, right? TC is PC, it depends on substance. As long as you define the species, the B is a constant, okay? And then similarly, if you rearrange the equation, you will see it's going to be a polynomial equation that is cubic on B, right? So that's why this is also a cubic equation of state, okay? Now, in the additional slide, we have some practice problem involving these two equations. You can actually go and take a look how to use these equations of state, okay, in real-world applications. All right, so that's virial equation of state, cubic equation of state for either gases, virial equation only for gas, but cubic equation for gas and liquids, okay? Now, more in real world, people can actually go a step further and then use generalized charts for gases to actually calculate this compressibility factor. So this is like starting from, let's say you starting from virial equation of state, Z is equal to 1 plus BP divided by RT. So now this equation is coming from here, right? But we are ignoring the higher terms. We just plug in BP divided by RT. So that's how you get this equation, okay? And then if we specify a species, right, which like I said, you can look at their critical pressure up, critical temperature up, right? And then P is basically equal to you just normalize your pressure to in relative to PC. So P is going to be equal to relative pressure times PC. And then T is equal to relative temperature times critical temperature, okay? And then you can combine these things, right? Since this is like a substance dependent TP PC values, you can combine everything together. So basically this B hat is going to be a material specific constant, okay? And then again, people already measure that for you already, okay? And then for this generalized correlation for B, B is going to be equal to some B0 plus omega times B1. And this omega is called a eccentric factor. And this eccentric factor is defined as omega is equal to -1 minus log PR saturation at TR equal to 0.7. So PR saturation is basically your P saturation divided by PC, critical pressure. And P saturation is the equilibrium pressure of a vapor above its liquid, right? So again, these values you can look up and then you can calculate omega, right? People already calculate for you for different omega values for different substances, right? You don't even need to calculate yourself. You can just look them up in the table, and I will show you how to look them up later. Okay. So now B0 is basically just like depends on your temperature, right? B0 is equal to these constant, but you have some temperature dependence, okay? And then B1 also has some temperature dependence. So as long as you know the temperature, you can you can calculate this B1 and B0 values, okay? And then again, like I said, right, the values of omega for some substances are provided in Appendix B, and I will show you a screenshot later, okay? And then now, because B hat is going to be have some B0 and omega B1 terms, basically you can do the same thing for Z. Z is going to have like some Z0, and then omega Z1 terms, right? And then Z0, if you plug these back in, and then you will quickly realize Z0 is just equal to 1 plus B0 times PR divided by TR, and Z1 is equal to B1 times PR divided by TR, right? And then again, Z0 is going to be a function of TR and PR, right? Z1 is going to be a function of TR and PR, right? So now, basically, these values are already compiled in the tables, right? Tables in the textbook, right? Table D1, D3 give you Z0, table D2 and D4 give you Z1. And then as long as you know TR and PR values, you can look Z0, Z1 up. Once you look Z0, Z1 up, you plug into this equation. And then if you know the species, you find the omega value, right? And then basically you can actually calculate Z for your particular gas at that particular TR and PR values. Again, T R and PR are calculated from your T and P by dividing them with PC and TC, okay? So as long as you know the temperature and pressure, right, you find TR, PR, you find Z0, Z1. If you know the species, you find omega, you calculate Z. And then Z is equal to PV divided by RT, so you can figure out the PVT relationship for that particular gas, okay? All right, So we already give you a walkthrough of this particular case, right? So basically, let's say we want you to use the generalized chart for gases to actually calculate volume, and we give you temperature and pressure of the system already, but we just don't know the volume for this particular gas. We want you to calculate, okay? And then first step is going to be you look up PC and TC and omega for this particular species, right? For example, methane, you can go to this table and then you find TC, PC, and omega values for this methane gas, okay? And then once you get TC and PC, you can calculate PR and TR, right? Again, PR is equal to P divided by PC. TR is going to be equal to T divided by TC. Once you have the calculated TR and PR values, like I said, right? Z0, you can look it up. Z1, you can look it up. So pretty much you know omega, Z0, Z1. And then basically you plug into this equation to calculate Z, right? The actual Z. And then from this Z value, you can calculate V. V is equal to ZRT divided by P, right? Now, if you remember, right, if Z is equal to 1, then basically that's how you calculate the ideal gas volume. But if this equation give you Z is not equal to 1, right, then your actual volume will have some deviation from that ideal gas volume, okay? So that's scenario 1. Now, scenario 2 is more complicated. Let's say we only give you the volume and temperature of that particular gas. We want you to calculate the pressure, okay? So this is trickier because, right, without a P, we cannot look Z0, Z1 up, right? Because we have to have temperature and pressure to look up Z0 and Z1 values, right? But we can still do calculate this, right? This is how we do that. First step is the same. And then now the second step, right? So TR is still the same, equal to T divided by TC. But here, the difference is that we don't know PR, right? This is actually what we want to calculate, right? You want to calculate this P. So, but we don't have this, but we know P is equal to ZRT divided by V, right? And then T we give you, so T is known, and then V is known, right? So R is constant. So essentially we know this part already. So we know P is going to be some constant values times Z, okay? And then PR, right? Since we know P is equal to constant times Z. And then PR is equal to P divided by PC. And again, PC we can look up. And then it's a constant value for a species, for a particular species. So in the end, we know PR is also some kind of constant times Z. And this constant is going to be RT divided by V PC, right? All these T, V, no, PC you can look up, okay? So we know P is some constant times Z, okay? So now in order to calculate P, you actually need to do some iterations, right? First, you assume Z is equal to 1, okay? Now, if you assume Z is equal to 1, then you can calculate, you know this constant, you can calculate PR, right? So now you have like TR, PR, you can look up Z0 and Z1 and omega, you plug in, and then you can calculate a new Z, right? And then you compare this new Z with the previous Z, which is equal to 1. If it's equal to 1, then you stop the iteration. You can just say this is ideal gas. But if it's deviating a lot, right? A lot means above the tolerance level, then you continue this iteration until you find your Z current value minus Z previous is smaller than a threshold. And then you can accept that solution Z. And then once you know the Z, you calculate V is equal to ZRT divided by P, right? Similar step. Okay. So these are how you can calculate, you know, PV, you know, you can find the PVT relationship. Um, you can calculate compressibility factor in two different scenarios using this generalized charts specifically for virial equation of state. Okay. All right. Speaking of the tables, right? Like I promised, I will show you some tables, right? So here we can see methane. You can look it up, right? Omega value, TC value, PC value, and also ZC value. ZC value we will come back later when we are talking about liquid. Okay, but for now, you just remember we can actually also look up ZC value. DC is critical compressibility factor. Okay. And then also VC is the critical volume, okay, of your liquid. All right, so these are the for when you're talking about gas behavior, then you are talking about PC, TC, omega, right? These are three values that you need to look up. And then same thing for Z0, like I promised, I give you some Z0. So here you can see, right? We have a table outlining all different PR values and then all different TR values. And then depending on your PR and TR, you can actually look up Z0 values. Same thing. You can look up like Z1 values based on particular PR and particular TR, right? So once you find these, you plug it back into these equations, right? Again, these are for very generalized chart applications, okay? All right, so that's for equation of state for gases, right? Specifically for real gas, right? Now, what about liquids, right? We also have like equation of state for liquids, right? For saturated liquid, for example, we can use Racket equation of state. Okay, so the mathematical expression for this is that V saturation liquid is just equal to VC. VC is the critical volume, basically the molar volume at the critical point. Okay, times ZC times 1 minus TR 0.2857. Okay, if you don't know the critical point so far, we will talk about that in the next lecture. Okay, but you just imagine it's a thermodynamic state. Okay, critical state. Okay, so basically so VC you already know, you can look up from the table in the previous slide, and then ZC you can also look them up, right? And then basically you just like, as long as you know your temperature, you just like plug like these two values you can look up for a particular species. And then as long as you know the temperature, you calculate TR, you plug back in, and then you can calculate your saturation volume, saturation liquid volume, okay? And then ZC, right, VC, ZC are just like compressibility at critical point where your pressure is equal to critical pressure, temperature is equal to critical temperature, okay? Or your PR is equal to 1, TR is equal to 1, okay? Now, if you look at this equation carefully, right, you can only see temperature dependence. Like I mentioned, if you have specified species, these two are just constants. But you have a temperature variable here. So this V actually only depends on temperature, but no pressure dependence, right? The reason why we don't have like too much pressure dependence is because usually these liquids are incompressible, right? Not like gas. Gas are compressible. So depending on pressure, right, your gas molecule will become closer to each other. You can actually compress it. But for liquid, not too much compressibility. That's why for this particular case, right, we don't have any pressure dependence here, okay? And then, like I said, right, VC and ZC, you can find them in the previous table. So just look at slide 13, right, DC and VC values. You look them up, you plug in, as long as you know T, you can calculate V, okay? All right, so that's pretty much all the equation of state that I want to cover, right? In chemical engineering processes, right? Again, virial equation of state, cubic equation of state. These are for gases, and also liquids for cubic equation of state. And then saturated liquid state, liquid is this particular equation, right? So these are the PVT relationship or EOS, right? Again, remember, once you know these EOS, if you know the heat capacity CP values, then you can actually calculate delta S, delta H, delta U between two states, right? By using integral, okay? All right, so now we talk a lot about real gases, ideal gases, right? What's the difference between these two, right? The difference between these two is actually quantified by so-called residue properties, right? For gases, we are talking about residue properties, but later in our next lecture, we are going to talk about liquid, right? Liquid, usually we call that deviation from like ideal solution to real solution. We call that access property to just differentiate, okay? But for now, we focus on real gases in this lecture. So we will say these are residue properties. So basically real is equal to ideal plus minus some correction, okay? And then this correction is called residue property. And by definition, right, the residue property or M represents a thermodynamic property. It can be any of these intensive thermodynamic property at T and P. Could be V, S, H, G, A, okay? And then the residue property, like I mentioned, is going to be the difference between the real and the ideal gas properties, right? So M real minus MIG. IG means ideal gas state, okay? And then this residue property, you have to define the temperature and pressure, right? It will depend on temperature and pressure. So it's going to be a residue property at that particular temperature and pressure, or at that particular state. At different state, you will have different residue property. So in the end, right, your residue property is going to be a function of T and P, okay? All right, so now let's first think about the residue molar volume, right? So residue molar volume is going to be actual volume minus ideal gas volume at a particular temperature and pressure, right? So previously, we already know how to calculate ideal gas volume, which is RT divided by P. And then the actual volume is going to be ZRT divided by P, right? So the residual molar volume is going to be ZRT divided by P minus RT divided by P. So it's going to be RT divided by P times Z minus 1. Again, Z, remember, right? Z is that compressibility factor. If Z is equal to 1, then basically your residual volume, molar volume is 0, because the actual gas or the real gas is actually behaving like an ideal gas, or adopt ideal gas behavior, okay? And like I mentioned, usually when our pressure goes to 0 or temperature is high, right? We remember the real gas actually recover the ideal gas behavior, right? So when you recover the ideal gas behavior, that means your residue property goes to 0, right? Because your real property actually recovered the ideal gas behavior when your system pressure is going to a small value, right? And all real gases, remember, all real gases behaving like an ideal gas at low pressure. By low pressure, we are talking about 1 atm, less than 1 atm. Certainly, you can assume they are low pressure, okay, or ideal gas behavior, okay? Ideal gas behavior, Z equal to 1, right? Again, VR is equal to 0, okay? So when the real gas behave like an ideal gas, you don't have any residual property or you don't have any deviation from the ideal gas, right? Now, why residual properties are important, right? So imagine we want to calculate the change in the thermodynamic property of a real gas between two states. Okay, so state one is P1 T1, and then state two is P2 T2. Okay, but we are talking about the real gas, right? We haven't dealt with this kind of like problem before. But what we have done previously is we actually have calculated the delta U, delta H, delta S for ideal gas, right? If you remember, right? So when we talk about ideal gas, we can actually set pressure is equal to zero, right? Pressure equal to zero, obviously you have ideal gas behavior. And then we already know how to calculate the ideal gas change, right? Changing U, H, S when you change from T1 to T2, okay? So if you look at slide 7, you should be able to figure out how to calculate this delta M, okay? Delta Mg, okay? So this you already know how to calculate. But now we just need to calculate the residual property here, residual property here. So basically by directly going from this state to this state in real gas state, what we are going to do is that we are converting this real gas while holding temperature constant. So we are holding constant temperature. We are going from real gas to ideal gas behavior by dropping the system pressure down to zero, okay? And then you maintain the ideal gas state, and then you heat the system up to T2, right, at pressure equal to zero. Okay, so this is going to be still ideal state. And then this is the change between two ideal gas states, right? And then once you change to T2, now you bring the pressure back up to P2 to achieve the real gas behavior, right? So basically your delta M by going through this is going to be the delta MA plus delta MB plus delta MC, okay? And then delta MA is basically you are changing from real to ideal. So basically it's going to be like final minus initial is going to be minus M1R, right? And then for here, delta MC is going to be final minus initial, real minus idea, so it's going to be M2R, right? The M2R minus M1R plus delta Mg, right? So this you already know how to calculate. Now the issue is that if you are able to calculate M2R and M1R, you can actually quickly calculate your delta M for your real gas. Um, uh, 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 okay. All right. So now let's give you some quick examples, right? How to calculate residue properties at constant temperature, right? Remember, residue property, we are talking like here in these steps, you only need to calculate residue properties at constant temperature, right? So here is constant temperature T1, changing from pressure P1 to zero, right? Or holding constant temperature T2, changing from pressure from zero to P2, okay? So that's how you calculate residue property at constant temperature, right? Basically, you do an integral from 0 to P, okay? So for GR, right? First thing first, right? Let's talk about GR. So dGr divided by RT is going to be VR divided by RT dP, okay? And then here at constant temperature, because we know, right? Let me see, yeah, here we have this relationship, right? dG is equal to VdP minus SdT, right? If we have constant temperature, then basically dg is equal to vdp, right? Now dgr divided by rt, t is constant, so basically is equal to vr divided by rt dp, okay? All right, so now we already know VR is this from previous slide. You just plug in, right? And then basically RT cancel. So in the end, it's going to be Z minus 1 divided by P dP. And then we want to calculate this GR. So basically, we need to do the integral from the ideal state to the real state. Ideal state is when the pressure is equal to 0. Real state is the pressure equal to P, right? So you can actually take the integral, right? So GR RT P equal to P real minus GR RT P is basically equal to 0. It's going to be taking integral from 0 to P, right? This whole thing taking integral from 0 to P, Z minus 1 dP divided by P, okay? So the ideal gas, you don't have any residue property. So this goes to 0. So in the end, GR divided by RT is going to be equal to integral from 0 to P, Z minus 1 dP divided by P, okay? All right, this again is at constant temperature, right? This is like what we care about in the previous slide. And similarly, I'm not going to go through the math, but you can actually read the additional slide if you are interested. But in the end, HR divided by RT is minus T, taking integral from 0 to P, partial Z, partial T, holding P constant, dP divided by P, okay? And then also at the end, right, SR divided by R is going to be minus T, 0 to P, partial Z, partial T, P, dP divided by P minus integral from ideal state, right, to real state, Z minus 1 dP divided by P, okay? We're kind of like combining these two terms, okay, S. All right. So now, once we know how to calculate the residue property, right, we can actually calculate H and S of real gas at any temperature and pressure, okay? So again, real gas is equal to ideal gas plus residue property, right? So you will know, right, H for your real gas is equal to H ideal gas plus some residue property. S is equal to SIG plus some residue property. And from previous slide, we already know how to calculate residue H using this equation and residue S with this whole equation. We just need to take the integral, right? But now the temperature is fixed, right? Then you can actually calculate the ideal enthalpy, okay? Now, you also want to recall these equations from previous slide. dH is equal to Cp dt for ideal gas, right? ds is equal to Cp minus divided by T dt minus R divided by P dP. So this is like for ideal gas, how the enthalpy change with temperature, entropy change with temperature and pressure, okay? Now we want to calculate entropy and enthalpy at a particular TMP, right? We can actually just like pick a reference state, right? So for ideal gas, right, the enthalpy is going to be the standard state at T0, P0, right? P0 is going to be 1 bar, for example, which is considered to be low. That's why the gas is behaving like ideal gas. And then you have a standard state temperature T0, okay? So for the enthalpy of your ideal gas, you are going to change from like this standard state to your actual T and P, actual T and P0. Again, you are holding this ideal state, right? So you just like ideal gas only change with temperature, right? So you just need to take the integral from T0 to T. T is your actual temperature, CPIG dt, right? So this is like this RHIG, right? Now you also want to calculate the residue property at this particular temperature and pressure, right? So like I said, the integral from ideal gas state to pressure, right? Actual pressure. And then here is your residue property. You just like plug in. Now remember, this is your H divided by RT, but here we want to have like HR, so you actually need to times RT. So that's why we have minus RT squared here in this equation, but this portion is the same, okay? And then in the end, right, this is your correction, this is your residue property, okay? So if you look at this integral, right, if you specify T0, then this part you can calculate, this part you can look up. And then if you know the Z, you can actually plug in and then you can take the integral, right, from 0 to P. So you can actually calculate your H at a particular TP state. And then same thing with your S, right? So S is going to be like, again, if you pick a standard state, it's going to be S0 IG. And then you need to take integral with respect to the temperature, right? Temperature is changing from standard state temperature to actual temperature. And then you also need to take integral with respect to pressure, right? So here is basically P0 to P, okay? And then you also need to take some corrections. Again, just a reminder, this is SR divided by R. Everything need to multiply by R. So minus RT, this whole thing, minus R, this whole thing, right? So this is how you calculate H and S at any temperature and pressure, okay? Now, if you go back to this schematic, if you know how to calculate S and H at T1 and P1, and you can also calculate S and H at T2 and P2. And then you can calculate the delta H and delta S between this state 1 and state 2, right? So you do the calculation twice and then you subtract them, okay? All right, so that's how you calculate the changes in these thermodynamic properties. But if you take a closer look at this equation, right, all these equations will contain CP and Z function, right? So this Z compressibility actually connects the real with the ideal, right? So all this is the ideal part. This is the correction correlating the actual with the ideal, right? As long as you know Z, you can plug in and then calculate everything else. Okay. Now, speaking of Z, right? You already know, right? Z is equal to Z0 plus omega Z1, and then here Z0. You can look them up when you know TR and PR. Same thing with Z1. You know TR and PR. You can find Z1, right? So pretty much like you can actually calculate Z as a function of TR and PR, right? And then you can actually plug in and then you can take the integral, right? Mathematically, it's going to be pretty complicated, right? But people already done that for you. That's why we can actually use these generalized correlations for HR and SR. So skipping a lot of math, you will actually eventually get HR divided by RTC is going to be HR divided by RTC 0 plus omega HR divided by RTC 1, okay? As long as you know TMP, you can calculate TR and PR, and then you can actually look this portion up or this portion up, and then again, omega is specific to a species, so omega is material dependent. TC you can look up. So essentially, we can actually quickly look up these values in table, and then you can calculate a chart. And then same thing, you can actually calculate SR, right, using a similar manner. So SR divided by R is going to be equal to SR divided by R0 plus omega SR divided by R1, right? As long as you know temperature, pressure, you calculate these and you look these up in these particular tables, okay? And then once you calculate the residual property, you couple back to ideal property, which you already know how to calculate, and then you get the enthalpy and entropy for your real gas at any temperature and pressure. Okay. All right, so this is just like the table outlining, right? HR0 divided by RTC as a function of different PR value and different TR values. Same thing for example here, right? This is like 1.5, and then PR is like minus 0.5, and then you have like HR0 is equal to this particular number, okay? And then same thing for HR1, right? Same PR and TR, you look up this value. And then same thing for SR, right? SR, this, you look up. And then SR1, right? You look up. And then you go plug back in to figure out the residual property. All right, so that's pretty much about it today. And sorry, the lecture went a little bit longer than the 75-minute slot, but hope you already understand the thermodynamic relations and also how they correlate to the thermodynamic behaviors. And also, more importantly, understand the difference between ideal gas and real gas, and how can we quantify that difference using residual properties. All right, I will see you at next lecture. Bye.